So let's have a discussion to reinforce intermolecular forces. So remember, the R is on the outside. So we're talking about forces in between two different molecules, not the forces that hold a molecule together. Those would be intra. For example, that would be an intramolecular covalent bond. That would be a nonpolar covalent bond. That would be a polar covalent bond. You can also have ionic and stuff like that. But intermolecular forces, remember, everyone has London dispersion forces. That is the result of the movement of electrons. The term you're going to see is polarizable. The more electrons you have, the more polarizable the electron cloud is, the greater the London dispersion force. So, the more electrons you have, the more polarizable the electron cloud is. In other words, when LDF happens, you're going to have a greater temporary dipole created. Then we have dipole-dipole. Remember, polar. You have to be a polar molecule for this. So H2 cannot dipole-dipole. That's a nonpolar molecule. All it has is a nonpolar covalent bond. O2 cannot do it. That's just a nonpolar bond. CO2, CH4, and SF6, they cannot. They do have polar bonds inside of them, but due to the shape and the fact that the bonds are of equal polarity inside of them, they are all canceled out, and when they are all canceled out, we're nonpolar. None of those can dipole-dipole. But carbon monoxide, ammonia, CH3Cl, SF4, that's a polar bond. It's not canceled. These polar bonds are not canceled due to the shape. These are not canceled due to the fact that all four of the bonds do not have the same polarity. Otherwise, tetrahedral molecules, when they do have the same polarity, they do cancel out. This is sea salt. They cannot cancel out. All those can dipole-dipole. And then hydrogen bonds. You have hydrogen directly bonded to NO or F. Water can. You have oxygen directly bonded to a hydrogen. Here, though, sulfur directly bonded to hydrogen, that does not work. So, just to talk about the magnitude of intermolecular forces, ionic is the strongest. Remember, you can use Coulomb's law, this little constant multiplied by the charge values divided by the distance between the charges squared. So like potassium bromide, that's a positive potassium, that's a negative bromine. There's an ionic force of attraction between them. And those are considered very strong. Ionic compounds have a high melting point. They're usually solids at room temperature. Then we have ion dipole. That would be an ionic compound interacting with a polar or dipole molecule like water. So KBr is like that, and then the negative part of the water would be attracted to the positive of the potassium, and the positive part of the water would be attracted to the negative part, and those interactions are called ion dipole, and they're pretty strong. Not as strong as straight up ionic, but they're still pretty strong when you're looking at things like just the force of attraction themselves. And then we have those found in our covalent molecules. So covalent, just all nonmetals are beneath your ionic. Hydrogen bond, dipole-dipole, LDF. But you have to pay attention to information that is given. We're saying LDF is the weakest, but remember, the more electrons you have, the greater the LDF, so you've got to pay attention. And we're going to talk about boiling point in a second here on the next page, but I'm going to go ahead and introduce it here. So all these halogens only have LDF, But by the time you get to I2, the LDF is strong enough. Iodine is a solid at room temperature. CS2 and COS, these are their Lewis structures. CS2, when we look at it, that is a linear molecule. Let me zoom in just a little bit here. It is a linear molecule. It has two polar bonds in it. Due to the shape, they cancel out and the fact they're equal polarity. All this can do is LDF. Here, that's a polar molecule. It can dipole-dipole. These bonds don't have the same polarity. But when you look at the boiling point, CS2 actually has a higher boiling point than COS. And like we're really going to see on the next page, the greater the boiling point, the greater the intermolecular forces. So CS2 only has LDF, COS has LDF and dipole-dipole, but according to the boiling point, the LDF of CS2 is greater than the combination of the LDF and dipole-dipole from COS. So you just have to pay attention to the information. So let's continue this thought about boiling point. Let me zoom back out just a little bit. So the greater the intermolecular force, the greater the boiling point, the lower the vapor pressure. And these are tied in with each other and vice versa. So let's talk about vapor pressure and boiling point for a second, and then we'll look at an example. So vapor pressure is the pressure of the escaping vapor of a liquid. And then, of course, we have atmospheric pressure pushing down on it like it's pushing down on you right now. Remember, we discussed to boil, the atmospheric pressure and the vapor pressure of a liquid have to equal each other. So, let's look at examples. H2S can dipole-dipole, and it has LDF. And to escape, H2S molecules would need to have enough energy when they hit the surface to break through and overcome the dipole-dipole and LDF that's trying to hold them in here, the attractive forces to all the others. Water, LDF, dipole-dipole, and it can hydrogen bond. So there are more intermolecular forces for water to overcome to be able to leave. So we would expect at the same temperature for water's vapor pressure to be lower than H2S's because there are more intermolecular forces for us to have to overcome. The greater the intermolecular forces, the lower the vapor pressure, the harder it is to leave. The lower the intermolecular forces, the greater the vapor pressure because it's easier to leave. But if your vapor pressure is low, that means you're really going to have to heat it up. You're really going to have to raise the temperature so that the atoms and molecules have more energy so that more can escape so that the vapor pressure will equal the atmospheric pressure. And that bears out. At 100 degrees Celsius, the vapor pressure of water is 1 atmosphere. That's why the boiling point of water at sea level, where the atmospheric pressure is 1 atmosphere, that's 100 degrees Celsius. That just happens to be the temperature when the vapor pressure of the water equals the atmospheric pressure at sea level. At 21 degrees Celsius, at a much colder temperature, the vapor pressure of H2S is huge. It's 17 atmospheres. It's really easy for H2S to escape, which is why its boiling point is so low. Negative 60 degrees Celsius is what that boils at. That's how cold it is for the vapor pressure of H2S to equal 1 atmosphere. So now to finish, one last thing that I'm going to introduce here is the idea of how intermolecular forces affect solubility. two things trying to mix together or dissolve together. And the general rule of thumb is like dissolves like. Polar dissolves polar, nonpolar dissolves nonpolar. Water is usually looked at as the polar solvent, called the universal solvent. So anything that's polar, water has at least a chance to dissolve it. And it can dissolve most things, not all, but it at least has a chance. Nonpolar solvent, usually that's going to be a hydrocarbon. Something like hexane is a very common example. Hydrocarbons are considered to be nonpolar. So a nonpolar compound would be expected to be easier to dissolve or mix with a nonpolar solvent. So an example, ionic compounds are very polar, okay? Because you have your cation and your anion. Water can dissolve some or most ionic compounds. Hexane cannot dissolve any. We'll talk more about solubility in another video.